This is section 4.3 notes, and it's going to talk about the atom and how scientists came up with kind of the model that we have today. So the first thing I'm going to do is I'm going to show students this video on Dalton's atomic theory, and this is the theory of how the atom was really kind of discovered. So I'm going to go ahead and play that.
Hey everyone, Professor Davis here from ChemSurvival.com and the YouTube channel ChemSurvival, and today I'm going to talk to you about Dalton's atomic theory. Dalton's atomic theory was devised by an English chemist by the name of John Dalton. He was working at the very beginning of the 19th century, and he's actually most famous for his law of partial pressures of gases, but he's also, or at least should be, equally famous for being the first scientist to truly use data to support the existence of atoms. Let me show you how he did that. Let's consider two very simple reactions, the likes of which you'll probably encounter in an introductory chemistry course. We can take oxygen and react that with two equivalents of hydrogen to create water. But water's not the only thing we can make from oxygen and hydrogen. If we combine them instead in different proportions, we can create hydrogen peroxide, the likes of which you might find in your medicine cabinet at home. Now, Dalton used reactions like this to demonstrate that there must be a fundamental, indivisible particle which is combining to make these materials. Let's take a look at how he did it. Looking at the top reaction, let's say that I start with 32 grams of oxygen. I'll need 4 grams of hydrogen to completely convert that oxygen into water. And when I measure the amount of water formed, I get exactly 36 grams. Now, you probably noticed that the sum of the masses of all the starting materials in this case is equal to the mass of the products. And this observation will actually hold for any reaction at all, any chemical reaction. Let's take a look at the bottom. 32 grams of oxygen can react with 2 grams of hydrogen, in this case to form 34 grams of hydrogen peroxide. Again, my masses should balance. We call this the law of conservation of mass, because in any chemical process it will always hold true that the total mass of all starting materials is equal to the total mass of all products. Now let's look at one more mathematical relationship. Let's look at the ratio of the starting materials to one another. In the top reaction we have 32 grams of oxygen and 4 grams of hydrogen. So I need 8 times as much oxygen as hydrogen by mass. This is something that Dalton could have measured. In my lower reaction, I have 32 grams of oxygen reacting with 2 grams of hydrogen. The ratio, 16. And these ratios are similar to one another. They're divisible by a very small whole number ratio, in this case 2. This is known as the law of multiple proportions, and it holds for a number of reactions in which we combine multiple substances to make more complex molecules, just like we're doing here. What Dalton did was to combine the law of conservation of mass with the law of multiple proportions to demonstrate that there must be some fundamental indivisible particle. In other words, you can't add a half of a hydrogen atom to a molecule. Therefore, you can't have a proportion that isn't either 8 or 16 in this type of reaction. This is what Dalton used to support his theory. And because it was his theory, he got to name these fundamental particles. And he chose the name atom from Greek words meaning not divisible. This is the source of the term that we use today to describe this fundamental unit of matter. That's all for now, everyone.
All right, so that is how how we have the term atom. That is how we know atoms exist. He was the first guy that did that. So he said, here's just kind of a short summary of that atoms are tiny particles of matter. He also said that atoms of each element are similar and different from atoms of other elements, right? Like oxygen is going to be different than hydrogen. Atoms of 2 or more different elements combine to form compounds. So in the video, they showed you like how oxygen and hydrogen could combine. So 2 or more different elements are combining to form a compound. A chemical reaction involves changes in the arrangement or combination of atoms. So they showed you that where like H2O looked a little bit different than the combination of H2O2, the hydrogen peroxide. And that's what we'll really get into. What we're really going to start trying to learn after this chapter is how do these things combine? All right, so then we have this chart here. So we just want to know about our 3 subatomic particles. And those are protons, electrons, and neutrons. And we've seen those a little bit in some of the work we've done. So the symbol for a proton, let me click in here, is P, and then they will have a plus sign. Now, I am not for sure on here. I think I might be able to, yeah, there it is. Let me go back, and then I can do this and do a plus sign. There we go. All right, so it's a proton, and then it's got that superscript. The location of protons are in the nucleus of the atom. They have a charge of +1, and they have a mass that is right at 1. Electrons, on the other hand, they have a negative charge, so their symbol, and you'll see me write this a lot, because honestly, throughout this chapter, or not just this chapter, this year, we'll talk about electrons way more than the other 2. And you'll see me write E with a little negative sign a lot, and that's what that means. It just means electron. Location of these guys is outside the nucleus. Their charge is -1. And their mass is 0.0005, so it's so tiny that we don't even use those when we think of the mass. Neutrons are N. Sometimes they'll just leave it at that, just an N. Sometimes you'll see where it'll have N0, and the reason for that is because it is a neutral charge. The location of this one is in the nucleus. But the charge is neutral, so there is no charge. And neutrons weigh about 1 subatomic, or 1 gram, 1 subatomic mass unit is what they call it sometimes. All right, so that's that chart. This is going to be really important. This we'll use throughout the year, so we need to know these things. And we'll have a lot of worksheets dealing with the masses, the charges, all that. Okay, so what happens when you place 2 positive ends of a magnet together? Guys, think about that. If you put 2 positive ends of a magnet together, they will pull apart. Now, in class, I'm going to do something, and it's where you put 2 pieces of tape on the desk, and you actually like stick them to the desk, the 2 pieces of tape, and then you pull them both up, and when you try to put them together, you'll see where they will bend away from each other. So it's almost like when you try to put 2 magnets together and they push away. So that's what is going to happen here. They push apart. And then if you place a positive and a negative end by each other, they will come together. And so sometimes at the end of class, if we have time, which this year classes are shortened, I'll do a blast from the past and play Paula Abdul, if you know who that is. She has a song back from when I was a little girl in the 80s called Opposites Attract, and sometimes I'll play that, so I'll help you guys remember opposites attract, which means if you're looking up here, protons and electrons, they're opposite charges, so they will attract, but 2 electrons will not, and 2 protons are not going to attract each other. So push apart, come together. Now those 2 pieces of tape, if I flip them around, or if I flip 1 piece of tape around, they will try to stick to each other. So when I do that, when I pull the tape off the desk, it causes electron movement. And those electron movements give this a slight charge, and that's why they will push away from each other or come together. All right, let's watch this next video on Rutherford. Also, just more discussing on how we have some of these basics that we have in chemistry.
The plum pudding model of an atom was one of the most widely accepted models.
And I will apologize right now for the accent. If it's a little hard to understand, this was the best one I could find.
All over the world for understanding the structure of the atom. However, several experiments performed by scientists to study the atomic structure showed astonishingly different results. They were contradicting the plum pudding model. This led many scientists all over the globe to reconsider the structure of an atom and study it again. Around the year 1911, a British physicist, Ernst Rutherford, carried out the famous gold foil experiment. He did this to understand the structure of an atom. The experiment was carried out by Rutherford along with Hans Geiger and Ernest Marsden. The experiment he performed was a breakthrough in the field of chemistry which helped him understand the structure of an atom in a more accurate manner. This is how the setup of his experiment looked like. As we can see here, he used a source of alpha particles locked in a lead container with a very small slit. This ensured that the alpha particles only came out through a small opening and travelled in a straight line. But why did he select alpha particles in the first place? Well, the alpha particles were having high energy and were heavier as well. So if we say the atom is like a pudding of positively charged particles with electrons embedded in it, then the particles will pass straight through it. This is obvious because the heavier particles will pierce through the lighter pudding structure of the atom and pass through it. This is what Rutherford thought. For this reason, their greater mass and energy compared to the protons made him choose alpha particles for the experiment. Next, he used a very thin gold foil on which the alpha particles would bombard. Why did he choose a gold foil? Well, a really thin gold foil was estimated to contain approximately 1000 atoms. Lesser the atoms, more convenient the experiment would be. Lastly, are we able to locate this circular band with a gap here? What could this be? Well, this is the screen. A fluorescent screen that would help us detect the radiation. That means the screen will glow or emit fluorescent light whenever alpha particles will hit it. So this is how the track of alpha particles can be traced. Now we're all set to understand how the experiment worked. The alpha particles were emitted from the element present in this box. These directly hit the gold foil. Now what should happen ideally? As we know, the Thomson's model suggested that an atom is a sphere of positive charge with negative electrons embedded inside it. That means it is expected that the alpha particles will pass right through the atoms and hit the detector straight. And why so? Because the mass of alpha particles is heavier than the mass of positive charges. That means they should directly hit the atom and move ahead through it. Only a very small deviation would probably be acceptable in this case. But is this what he observed? Not really. He was astonished to get unexpected results. What results did he get? He found that most of the fast-moving alpha particles passed straight through the foil and hit the detector. However, some particles got deflected by small angles. And lastly, to his astonishment, few alpha particles also rebounded. Now, how can this be possible? These three observations made Rutherford think that the plum pudding model is not really correct. Based on the conclusions he had, he put forward the new hypothesis explaining the structure of atoms. What were his conclusions? Let us have a look at the conclusions by Rutherford, followed by the new atomic model put forth by him.
Alright, so basically what happened is they originally thought an atom was just had like some negative particles all the way through it, and that when you put, I think of it this way, and this is how I'll explain it to the class. If I were to stand here and a football player were to run at me, they're going to get through me. They're going to get past me. That's what's going to happen, and that's what they thought was going to happen because of this plum pudding model. Now, if you get me and every kid in this class to stand together and lock arms, and not just in a row, but like a circular, like we all stand together, and they're going to have a harder time getting through us, and they maybe get deflected and bounce off. That's what happened, and that's what surprised them. They didn't think that would happen. So it made them kind of re-look at everything they thought about the atom, and this is what they came up with because of this gold foil experiment. They have this dense center of protons and neutrons, and what was happening is this alpha particle was hitting this dense center and bouncing off. And then they realized that these electrons were actually on the outer edges in these clouds. So that is how we now have what we know today as the atom. If you guys need anything, let me know. We'll have section 4 notes in a day. Bye.